So good afternoon, everyone. I'm not sure what the music did, but as soon as the music was played, everyone walked out the end of the building, so that's kind of interesting. So this is going to be a slightly different discussion than the last discussions that people have had. And really, it's almost a plea to the organization and the industry in terms of how we think about things and how we talk about things. And really, when you look at the title of what I've got here and the coming hour and a half, really the discussion we've got is about, actually we need to think about materials for the maker class, and it's about the pursuit of the impossible. The previous speaker made the point about how do we think about addressing the impossible. And really over the past few years in Owens Corning, we've really tried to change the conversation about how we talk about materials and how we view this industry. Okay, so unfortunately we're meant to have sound for that as well, but never mind. So really for me the question becomes is how do we start to think about how do we help the customers to make things and make impossible things? So really for me the theme of this 1.5 hours is really how do we change the conversation that we're actually having within this industry, and how do we actually start to think about changing the conversation from talking about this, which is if you walk around the show, what you're going to see is people having pictures of this and pictures of parts and pictures of bits. Really, how do we change the conversation from what we make, what we as the consumer or the producers in this industry make, and how do we change the conversation to what we enable? What does this industry enable? It's not what we make, it's about what we enable. And really for me, as you step into this industry, and if you come from other industries, what we talk about all the time is we talk about how complicated it is, how complicated composites is, how we've got all of these steps and all these processes we need to think about. And really the question for us and the question we need to address is how do we move from complicated to inspiring? How do we help people think about what's possible, not what's impossible? How do we help them to produce stuff that they actually want to produce? And how do we enable a new generation of people to produce things that they really can imagine, but we as the older generation have never really thought about how to achieve? So really for me, the other thing that we think we need to reflect on as an industry is about, we spend a lot of time as this industry speaking about ourselves. If you walk around the show, you'll see people presenting about their company, how they do it, how big they are, how long they've been in business, et cetera, et cetera, et cetera. And really we talk about us and we don't talk about the people that are actually using our materials and actually changing the world through the use of our materials. So for me, this is a plea for this industry to think about how we start to think about the people that are actually going to drive the growth of this industry and the future of this industry, and less about the people that are actually in this industry today. And I think, if you start to work with the younger generation, what you're going to start to see is that they operate in a different set of rules than we do. They believe they can do things that we don't think are possible. And really, these are the people that are going to set the rules of the industry in the future. And really, for us, it's about how do we enable them to deliver material solutions to make this happen. It's not about what have we got on our booth. And really, for me, this point about we as an industry, we need to sit there and we need to start to think about how do we provide the materials and the expertise and the capability to support them to actually make their ideas possible, so they can be bold and they can start to drive the future of this industry forward. And really for us, we have a tagline in Owens Corning, it's called Making Possible Things. Really for us, this is what the goal of our company is becoming. It's about how do we help the industry start to make things that people thought were previously impossible. So today, what we've lined up is a kind of an unusual event. And really what we wanted to talk about is we wanted to talk about technologies and trends that were going to help people to make things that weren't possible. And really we're going to go through, we're going to have Paul from Ultimaker come and talk about really what's going on in 3D printing and how is 3D printing going to drive the future of our industry. We're going to have Marcus who's going to come and talk about how do we actually move this industry from a boutique, cottage, artisan industry into something that's actually viable, that enables people to make big structures that really can start to drive the penetration of composites. Emmanuel's going to come from Owens Corning to talk about the next generation of 3D printing materials. And then basically I'm going to close out with a few thoughts and comments about this event and what we've actually achieved through it. So what I would say is the future's up for grabs. We can do whatever we want. What we've got to do is we've got to move from being constrained from our own thinking into thinking about how we're actually going to enable the material revolutions that are going to drive the industry forward. And to do that, we're going to need people who are embracing and driving new technologies. So with that, I would like to introduce Paul from Ultimaker to come and tell us about what's really going on in 3D printing.
Perhaps could you start the next one? Well, before we start, good afternoon all. That's the way to do it. I wouldn't know that. Yeah, sure. Thank you very much. Okay. Good afternoon. My name is Paul Heiden. I'm responsible for the product at Ultimaker, and Ultimaker builds 3D printers. What I'm going to try to tell you today is that these little things will have an enormous impact in the way how you work, the way what you're doing, the way how you produce things. And seriously, I get it. When you walk over this huge conference, you will probably think such a small thing will never make a difference. Well, actually it starts small. And it reminds me very often, I have that age, of people saying that the mainframe was the best computer you could think of. And today we use laptops, we use all sorts of small things. This is what it really starts with. I think that local digital manufacturing, what 3D printing can do, is truly revolutionary. And I know these are big words, but what I will try to do today is explain to you a little bit of what we see happening, how organizations adopt this, and how people start using this in a successful fashion. I think we're part of a new industrial area. I at least learned that when you make one, that's always far more expensive than you make thousands of 10 or 10,000s. And if you really want to drive the product cost down, you have to mass produce. And just imagine what that means. It means that you have an enormous inefficiency, that you need to bring all sorts of stuff to central factories, and from factories you need to bring it out to warehouses where you need to store it. There's really essentially an enormous inefficiency in that way of producing. And just imagine what it would mean if you could produce only when it's needed and where it's needed. And I will give you several examples today of how that will look like, what the future actually will look like. And probably you will tell me, okay, I'll be listening, it's probably an interesting story, but it's still years away. Well, not really. And one of the most inspiring examples that I'm aware of is Atelier Stern. It's a garden shop in France. They have about 400 locations. And what you see here, again, is small, a fuel cap. But what they're essentially offering here is that if you sit down and you're mowing your lane somewhere and suddenly you need a new fuel cap, for instance, then with this fuel cap, you can simply order it at a web shop, and the web shop at Atelier Sterren will then somehow ensure that the thing that you need is 3D printed somewhere near you. And while you drive there, it's being printed, you pick it up, and you can immediately use it. So imagine what happened there. We continuously had this digital part, we continuously had the thing in a digital fashion, but only when it was needed, we send it out, we let the software fly to a machine, the right machine, and at that very moment it is produced when it's needed and where it's needed. Now there is something else. In 3D printing, it was good fashion to print in PLA. But you cannot print a reliable fuel cap with PLA. Nowadays, a good 3D printer will support many materials. I'll talk about that later. And in this case, with X-Strand from Owens Corning, Atelier Sterren is actually capable of delivering the strength that you can use this, that you can actually use it in your mower and immediately put it in. And I get it, it's still small, but just imagine what the promise is of this sort of scenarios. That local digital manufacturing will make you completely rethink how to drive product costs down and margins up. And essentially, I'm in an easy market, because if you don't think about it, competition certainly will. Everybody is thinking about this, and what I currently see is that particularly larger enterprises are making plans to implement 3D printing and make it an integral part of the way how they view logistics, the way how they view warehousing, the way how they start solving the needs of customer faster and right at the moment that somebody will need it. A little word on Ultimaker. Ultimaker didn't exist 7 years ago. The market at the time was completely blocked by patents, and 3D printing was carried out by Mammoth. It was completely protected and you couldn't do anything. Then the patents went, and suddenly a complete new industry came into existence. Ultimaker is only 7 years old. We're this small. But then at the same time, we have about 150,000 machines in the market. And our users are professional users. They know what they want to achieve. They're not making masks, they're not making puppets. They are truly using this in a professional fashion. And what we are all about is that we want to accelerate this transition to local digital manufacturing. You could safely say that any large company you can think of, apart from a bank, is using our 3D printers. And the reason they're doing that is because they all share one vision. And I've tried to visualize this vision. If you look at traditional manufacturing, by nature, because you need to produce thousands in order to make a cheap product, by nature you need to centralize. So what do we see in the world? We make compounds, we make all sorts of bulk material, we ship it to China, there we make something, we ship it back, we store it in warehousing, and we're waiting until somebody needs it. This is the way that we currently do it, and it's very difficult to imagine that you actually can do this in a different fashion. You could also do it in a different way, and then the factory becomes something entirely new. It becomes something where engineers sit and they design digital parts. And they design the equivalent of a physical part. And instead of making that part and storing it in a warehouse, they store what we like to call G-code. And I'll get back to that, what that is. And this G-code is flying over the world to those places where people need a certain product. Now, G-code is a CNC word, it's an Ultimaker word, and it is the toolpath that in the end determines how a machine should behave in order to produce a product. And what we like to tell is that think about not just producing, but think about instead create the right G-code and have this G-code fly around the world. We spend a lot of time thinking about 3D printing. And I get it. If you were to tell me today, well, a digital factory, isn't that far-fetched? Perhaps it is, but you start small. You start selecting those parts that you can actually do this with, and everybody is doing it, and they all go along the same lines. What I'm showing here is the bell curve of any part. It's the life cycle where you start developing something on the left-hand side, and then slowly you go to mass production, and from mass production you go to spare parts. Now, what we learned so far is that 3D printing was particularly adopted in the development stages, in prototyping stages. And it simply accelerated the process of creating something. Instead of making a tool, and that would take about 60 days, have it made in a workshop, people would push the button in the evening, and the next morning you could talk about something. It would actually be there. That's how this all started. And then slowly you see this movement of flowing over, and you currently see that 3D printing is being used in functional prototyping. You currently see that 3D printing is used to create tools in manufacturing. You already see that, and Atelier Sterren was this wonderful example, you already see today that people are starting to produce spare parts. Not 1 million at once and then start having them in a warehouse, but instead make them when they need it. And if you think of it, the steps are extremely straightforward. So you start with prototyping, then you go to functional prototyping, and the machine needs to support that. But once you're in functional prototyping, you also have the model, you have the G-code, you have the virtual part that you can also drive spare parts with. Once you're able to make truly reliable functional parts, suddenly the biggest market of all opens up, the biggest value of 3D printing opens up, of local digital manufacturing, make things where you want to make them. At a dealer, not centrally in China, on a ship. I'll give you some examples there. So this is something completely new, but it's already happening. Perhaps you recognize this, but I always like telling this. We only exist for 7 years. And in 2016, we introduced a machine called the Ultimaker 3, and suddenly we saw an enormous change in the behavior of our customers. And what we noticed had happened is that people who were trying 3D printing at home, literally at home, just trying, typically the engineer, the tinkerer, trying to do things, he would take it to where he works, and they would start using it. And in the beginning, they would use it every now and then. But once you start using it, people start understanding, hey, I can use it for this, I can use it for this, I can use it for this. And that's exactly how we saw it being adopted. So people were literally bringing it in. And nowadays, in most of the offices of any larger enterprise, you will see an Ultimaker. And it's about to happen, it already happens, that you will see a 3D printer anywhere where you would see a CNC machine. It's just there. It's an other production. It's an alternative to extractive production. And you already see it being used in a factory, not necessary for end parts, but to create tools. It's pretty impressive, but today Volkswagen is doing this, BMW is doing this, Ford is doing this. Look on the internet and you will see that all these companies are building tools for their operator on the manufacturing floor. And the reason they're doing that, if you really ask them, and we do a lot of research in that field, if you really ask them why they're doing it, they say because it works so much better with our operators. They ask something, can we change this? Can we make it a little bit easier? And the next morning, they are able to provide the right tooling for somebody that can start using it where he works on the line, and immediately it will show value. So apart from the fact that you increase the speed from 60 days to 1 night, it's above all the fact that you're more meaningful for others that made these people start introducing 3D printing. And today, many of the large companies are doing that. The reason that 3D printing is particularly taking off with larger enterprises has to do with the fact that 3D printing is not really easy. It's not so much in the printing itself. Printing is easy, you push the button and it works. But what you need is material knowledge. What you need is CAD knowledge. And so what we currently see is that the speed of adoption, the acceleration in the adoption, is particularly there with somewhat larger companies that start using this and start seeing, well, is this a material that I can use? Is this something that I can 3D print? Because they have the CAD knowledge available, they have the material knowledge available. That's happening in the factory, but still, if you look at the use cases, it's still a pretty dense workflow. You talk about CAD, you talk about slicing, so preparing the G-code, and you talk about printing. You could do it in this space, easily. But if we talk about the real value, we talk about distributed manufacturing. And that's happening as we speak. And what we see there is that no longer the champion brings the machine from home into the office. It's somebody that's appointed. It's an engineer, a young engineer usually, enthusiastic about 3D printing. He already learned that. And he will start using it. And then what you see is that although people usually immediately start with distributed manufacturing, they will immediately start bringing printers into a network outside of the place where they create the G-code. You quickly see the growing of a competence center, where people are really good at preparing prints, where people are really good at creating G-codes. That's what we show here. And I think that probably one of the most impressive examples that I can think of is, in this case, the Dutch Navy. And it's not about the Navy, it's about the ship. And just imagine what they're doing. Every ship has a 3D printer on board. And because it's FDM, the technology that we use, it doesn't matter that the ship moves. Even an FDM printer will print even with wind force 10. It doesn't matter, it simply works. We have impressive views there, and people are using it on a ship. Now just imagine what that does. Instead of having a helicopter fly in, or just sail back to a harbor, people can create the things that they need. And so we started with some small ships, and then slowly it expanded. They started in 2015, and today every ship has a 3D printer on board, and they use it for everything. And again, it's small. It's small things that people make. And at the same time, what you see, and I think that's already telling with when you think about 3D printing on a ship, in the beginning, people were just using it as another tool. And some things happened that were rather unfortunate. So people would repair a kitchen tool, for instance, with not so very food-safe material. People would try to repair a hose with not so very high temperature material. So what you saw is that there was a movement from distributed and then back. Not so much from the printers, they were there, the value of a printer as far away as possible, close to the customer is of course what you want, but the competence was created centrally. And this is what we consistently see. If there's anything going on today, it's the creation of competence centers. It's the creation of teams of application engineers that know how to identify an opportunity to 3D print, that understand how to make things from CAD into an object that is 3D printed. So let's look a little bit closer into the digital factory and what it actually means. I think you remember this case, right? It's now the third time that I mention it. But just imagine what's going on behind this screen. I've tried to visualize it as simple as possible. So you got somebody who has a mower and he needs a new fuel cap. He will order this. Ordering means that there is an instruction sent to some sort of a virtual warehouse. The virtual warehouse will make sure that you pick the right G-code. the G-code will be sent to the right machine. It doesn't make sense to end up with the wrong machine. It really needs to go to the place where somebody is nearby. So there is an infrastructure in place that makes sure that the G-code travels exactly to the right spot. At that spot, there are the right materials. If you want to make a fuel cap, you better make it from reinforced materials, so that should be there as well, because it's part of a service to your customers. Now, what happens at the same time is that you need to fill this virtual warehouse, and you need to fill it with G-code. And this G-code, making this G-code, as I said, is a somewhat complicated case where you need application engineering capabilities. And that's where I want to dive a little bit deeper today. Ultimaker is not only making printers. We also bring to market something called Cura. And Cura is software that generates the G-code, generates the toolpath that the printer uses in order to make something. Cura has about 3 million users. So it's obvious that Cura is not only used for Ultimaker machines. It's also used by students with cheap machines just to learn things and see how they can adopt 3D printing during their study. On the complete other side, it's also used to build houses. Concrete printing is also carried out with Cura. Huge parts that people build, even yachts that people 3D print. It's currently happening in Italy. It's all done with Cura. Cura creates the toolpath for a robot arm that prints, for huge printers that print, for Ultimakers that print, for cheap machines where people start learning this. Now, Cura needs 2 inputs. One is the CAD file. And the CAD file is then sliced, and the slicing helps you to exactly determine the coordinates of where the print head needs to go. But at the same time, that isn't sufficient. If you would put some material on a 3D printer in combination with the G-code, chances are at least 50% that it fails. And the reason is that every material requires different settings. It requires a different way of melting, a different way of drying up again. And in order to do that right, Cura offers about 350 settings. And per material, it would usually take about 6 months to get all these 350 settings right for one material. So we felt this is no way to go. Some people felt that this is the reason why you need a closed material system. So other companies present here will tell you, yeah, we have a closed material system because it always works. We have 4 materials that you can choose. But everybody is aware that you pay a huge margin to these folks. And what's worse, if you really start using 3D printing as a distributed manufacturing tool, you don't want this lock-in with one material supplier. You don't want the lock-in of the materials that are provided by the 3D printer provider. This must change. And that's exactly what we did. We made sure that we had a proper integration with CAD systems. That's all straightforward. Here are just a few. Today we're announcing our entering in the dental market. And again, there you will see connectivity with all the dental CAD software. But what's far more important is this. And you might think, that's not nice, Mr. Heiden. You're here on invitation of Owens Corning, and what are you doing? You're showing all the partners that work with Ultimaker. But hey, this is in the interest of every customer in the world. It's not about one material. It's about the properties that people are looking for with their part. The properties that people try to establish with a part. Sometimes it's transparent, sometimes it's food safe, sometimes it's strong, sometimes it's soft. It doesn't matter. We want to make sure that you can use the materials that you want. Now, I told you a few minutes ago that making a material available for 3D printing requires the right settings, 350 in all. That's a serious barrier. So what we did is we created software, and any material supplier in the world can become partner of Ultimaker. You will get the software, and instead of 6 months, you'll do this in 2 weeks. Within 2 weeks, you're ready, you have your printing profile. The printing profile is made available in Cura, so 3 million users can start using your material. And what you currently see in this list is all sorts of specialized companies that offer something that people might need. We opened our material program in November last year. This is the number of material partners in January. It's growing every day. And also what you currently see in Cura is the number of materials that are actually released, or at least the printing profiles released for our users. And soon we'll be talking about hundreds of materials available for printers. And that, in my view, should give the real, well, strength, the real power to make sure that 3D printing can actually be used. Some final words. As people are asking me, okay, I get the point of digital manufacturing, and to be honest, everybody gets that. There's nobody telling me what a nonsense story. They just wonder how to start. And what I did is just say, okay, there are a few things that you need to watch out for. And these things boil down to the following issues. First of all, you want to start with an easy machine. It mustn't be difficult. You want easy to use software. It mustn't be a barrier for adoption. If you have an R&D manager that wants to train 10 people, just make sure that you have the type of software that's easy to use, easy to adopt. A second one is you need to already think about your infrastructure of printers. And it's difficult to imagine that you would have an infrastructure of tens of thousands of printers, and that's not weird in automotive where you have thousands of dealers that would all have a 3D printer to print tools, to print small parts. But it must be affordable, right? It should be something with low maintenance. It should be easy to use. It should be something that people can use without training. There shouldn't be any post-processing. It would be absolutely ridiculous to ask of people that are working at a dealer that they can deal with poisonous resins, that they can deal with all sorts of difficult handling. You should choose a technology that allows you to take it off the build plate and immediately use it. Very important. Needless to say that I feel, don't ever start with printers that have a closed material system. It will kill you. I heard this story literally from a company that adopted 3D printing, and then they found out that they could only use one material, and they simply stopped the whole process because they didn't want that dependency. And the good news is we came in and they could proceed. And finally, what is very important for us is we collect people. We try to mobilize people. We have literally millions of people that contribute to the quality of Cura, that contribute not just in terms of software, but also help each other in getting better at 3D printing, and that helps us again to put in the machine very good, to put in the world machines that really work and can help you harvest the values of 3D printing. Thank you very much.
So I'd like to say a big thanks to Paul for actually giving us that overview. I mean, what I would say, that's fantastic. I mean, what I'll say from personal experience there is something really very interesting, which is, I mean, as a company, we use 3D printing. I mean, probably everybody here uses 3D printing. What we use it for mainly is the optimization of our manufacturing plants. And last year we printed 11,000 different parts for our manufacturing plants based on those printers. And those printers don't stop. And that's the key thing for us. You've got to have a robust system. You have to have a good input material, but you have to have a printer that's reliable and never stops. And I think what he's talking about building a system and an approach and a material strategy that actually is going to enable the introduction of transformative technology for the composites industry. And what I'm going to do is I'm going to hand over and introduce to Emmanuel Vacon from Owens Corning, who's going to talk about the introduction of a new material. But talk amongst yourselves for 1 or 2 minutes because we seem to have some technical problems.
So good morning, ladies and gentlemen. And thanks again, Paul, for sharing your vision about 3D printing and the global picture. It's really appreciated. Thank you very much. So I'm going to talk here a little more about material. My name is Emmanuel Vacon. I'm an engineer in innovation since more than 20 years in the fiberglass industry. And since the last 3 years, I've been leading a team of experts in 3D printing. And the team has developed a material for high performance material for engineering application. And this material, or composite material, they can be used in FFF technology or FDM technology. So they are commercialized under the brand X-Trend. So 2018 has been a very exciting year for the team and for the 3D printing in general for us because despite the fact that we launched our 2 products early this last year, so the polypropylene and polyamide 6 glass reinforced with 30% glass fiber, we had the opportunity to participate to multiple international fairs all around the world. And among these fairs, X-Trend has been awarded twice. Once internally, an internal OC contest that we were participated, and another one at CAMEX, and we win in the combined strength category. And also this year we announced our alliance with Ultimaker. So X-Trend is part of the material profile of the new S5 Ultimaker, and that's really a really good thing for us. And on top of that, of course, there is a user at the end. We receive a very good feedback from our end user regarding this new material, this new composite new material, because it's opened a really new application thanks to the high strength and stiffness of this material. So let me explain a little more what is X-Trend and what are the value of this product. So far we have 2 products available, a polypropylene and a polyamide 6, both on glass fiber field. And they have been designed really to improve the printability. It means that this was really one of the outcomes of our development. For sure, when you develop a new material, you have to really take care about the performance itself, the printability, but also the manufacturing of the product itself. So this material is really a consensus, a mix of everything. So it has a superior strength and stiffness thanks to the glass fiber that is in it. It is short fiber, and the fiber has a special surface treatment that is make compatible the fiber with the matrix. So that means that each product has a different fiber with a different chemistry to make sure that we have the perfect bonding between the matrix and the fiber. And this leads to really the high performance of this material, and also the excellent layer adhesion that we can have on this material. So the next generation of printer that Paul talked about, the S5, is perfectly designed to print this material. Now I would like to talk about some application for X-Trend. So these are functional application. So let's start with the left part of this slide. Athletics 3D is a French startup that has been created maybe 2 years ago. and they are designing and printing sport equipment for high-level biathlon athletes. And here you can see on the picture a customized rifle grip made with polypropylene, X-Tron polypropylene. And here the value is that it's perfectly adapted with the athlete morphology. So it's lighter than wood, which is the standard product that is used. And it also meeting all the requirements regarding the low temperature resistance, because it is used during the winter sport. And a lot of athletes at the last Olympic game used that material during the game. So the value is really the customization here and the strength of this material. On the right, it's another example in a sport race. So you can see the exterior mirror housing on this Corvette. The red part on each side of the car has been made with polyamide 6 and with a very nice surface treatment. And if you have the opportunity to stop by our booth, J39, you will see the part with the coating. It's really nice. And it has been designed by Pratt & Miller, which is, they are involved in Corvette racing. And it's a very challenging part because, of course, you have to create a complex shape because of the aerodynamics constraint. But also you have to consider that inside you have all the motor, you need to fix it, and this part needs to resist at a speed very close to the 300 kilometers per hour, which makes it very challenging to make, and they succeed in it. Inside also, in designing this part, they have been able to reduce the number of parts to the minimum. So it's only one part, and this part is including all the support, all the stiffening ribs to make it really strong. So a very good application, very nice example. Paul talked also this morning, just before, about the importance of using 3D printing in our industry, and Owens Corning is doing that a lot. We have so far 2 labs dedicated to 3D printing with almost 30 printers in action. And more and more, now that we created awareness in our company that this technology can bring a lot, we see more and more requests, demand from our operation to create tools, jigs, fixture, or even spare parts, because now it's coming to replacing parts because they don't have the time to wait for the metal replacement. And in a lot of cases, you can replace reinforced plastic, metal with reinforced plastics. And it is also very demanded in innovation, because all our innovation team to create new sensor, to create new mimic test, or to create new prototyping now coming to us and ask. They just draw a simple sketch, and a day or 2 days after they have their part, and they can continue their project. So an easy way to accelerate the development time. So, okay, what's next now for X-Tron? So I'm sure you're all familiar with this well-known pyramid of thermoplastic. Let me explain just a little. So it's divided in 6 sections. The left, the semi-crystalline polymer. On the right, the amorphous one. And the more you go from the base to the pyramid to the top of the pyramid, you go from the commodity plastic to the very high performance thermoplastic. So you see a lot of acronyms. I'm sure you're familiar with it, like polypropylene, PLA, etc., and so on. And now, if you consider the material available for FFF, you can see that there is a lot of material that can be used in a FDM technology today. And this is one of the big advantages also with, if you compare FDM with SLS or SLA, so selective laser sintering, stereolithography, where usually you can use 2-3 products with this technology. Here you have a massive choice, and a lot of these products are reinforced with carbon or fiberglass. So now more and more we are seeing also printers that have the capability to print all this material. So a few years ago, most of the printer was only capable of printing PLA and ABS. It was open platform, no protection and nothing around the printer, and very simple printer, simple in the design, but you need to have a very solid background in mechatronic or software modeling to operate them 6-7 years ago. Now it has totally changed with the last printer and the new printer, because they included in their setting now the material profile. So you simply have to select the material profile that you want, and all the parameters will be populated into the printer. For sure, it's still difficult to reach the top of the pyramid because you need technology that is really complex, because to print PEEK or PEC or the PEC family or PEI, you need a heated chamber close to 250 degrees C. You need mechanics that are very stable at high temperature. But let's say that everything is moving from the bottom to the top right now, and the printer manufacturing are doing the same. So they started at the base of the pyramid, they are moving at the second level now, and they are going to the last level, and the material is becoming more complex, more technology, and it's really becoming an industrial tool, an industrial machine. So, moving up in the polymer pyramid, this is something also that Owens Corning is doing. So far, as I told you, we have the polypropylene available. We move to the next level with the polyamide 6. And now we are proud to announce a new product. It will be a polycarbonate, always reinforced with fiberglass, because this is what we are good at, to develop a composite material for 3D printing. And these are the characteristics of this new product. So we developed it mainly to have a flame retardant and UL94V0 product at the product range, in our range. So it passed all the tests, so that's great. We are still waiting for the final certification because it takes a long time, but it passed all the tests. Very good, an excellent heat deflection temperature, very good dimension stability, thanks to again the fiber that helped to reduce the CET, the coefficient, the expansion coefficient, thermal expansion coefficient, sorry. It's a very good electrical insulating material. And so in general, it is developed for functional prototyping in very demanding application, mechanical engineering, automotive, and electronics. This graph is a simple graph positioning the three products of Owens Corning, Xtron versus the most standard product. And against the value is the tensile strength, the stiffness. The polycarbonate is a little lower in mechanical properties than polypropylene or polyamide, but it has a higher HDT, heat deflection temperature, that makes him alone, that will allow maybe for application like mold, footprint for mold, or over molding with composite material. You know, we are still looking for application for this material, and I know that this is the way we are working. When you propose something new, it will open for new application. Even if we already have some idea on what to do with this material, no doubt that it will open a lot of other application and other possibilities in the 3D printing world. So this material, would say, is in the beta test phase. So the material is ready, but is not commercially available now. So it will be a commercial end of May or in May 2019. But if you are interested to test it before, you're welcome, and we can provide you some sample. And on the other side, we are expecting your feedback. I'm done with the presentation. Thank you. If you have any question, I will answer. Thank you very much.
Thank you, Emmanuel. It's really interesting. So again, we start to move the material boundaries of 3D printing to actually support our customers in actually the ability to make interesting things. And with that, I'd like to hand over to Marcus from Airborne. And really, I mean, for me, Airborne is really a cutting-edge company where we're talking about how to transform the manufacturing process of composites. So with that, I'd like to invite Marcus up onto the stage to tell us about the future.
Thank you very much. So I'm from Airborne, and I found the presentation of Ultimaker very interesting. We have two Ultimakers in our company. We do automation of composites and digitalization, and we use the technology to print parts that go into the machines that we supply. So we come from a bit different world. We come from the more traditional composite manufacturing world with tape laying and cutting and sandwich panels. And we try to digitalize that way of working. So the story is a bit similar to Ultimaker, but from a different angle. So Airborne, we are a company in the Netherlands. It's a bit a Dutch day here. We had earlier a country on stage program with the Netherlands, so it's apparently a theme today. So we're 20 years old in advanced composites, background in aerospace, maritime, offshore. And we have what we call a digital factory for composites. It's a field lab. It's an environment to explore concepts for digital manufacturing. And that's a collaboration that we started together with Siemens, who know a lot about factory automation and digitalization. And we bring the composite know-how. SABIC is a partner for material science, University of Delft, and also KUKA for the robotics. So here you see the typical parts that we have been making for 20 years. In aeronautics, in space, we are the European market leader in solar panels. We do repair of helicopter blades. We have developed technologies, ship propellers, all kinds of technologies. At the moment, we focus much more on automating composite manufacturing in cells, and I will show some examples later, but also in end-to-end automation. So what we like to do is to build fully integrated production lines where material goes in and all the steps that you need to do to make your part are automated and the product comes out. So more as a composite company, we're not so much a machine builder, but what we're trying to do is use our know-how of composite manufacturing to make parts for clients, but more and more to supply them with automated processes and also to go into digital manufacturing. So here you see a couple of units that we have developed and that are now standard solutions. So for us, these are building blocks that we can use and supply to our customers. Automate honeycomb potting for sandwich panels, automate laminating cell, pick and place, which is a very important building block, and also automated kitting. And I want to show you a bit what these systems are. So the first one, and you can see this one live at the Aerospace Innovation Planet. We have the whole system there and it's working. Is an automated kitting system. So if you use composite materials, typically you cut the material into different shapes and plies. And if you want to do that efficiently, you need to nest the plies to lower the material waste. The issue is then that the plies come in a different order from the cutting table than what you need for laminating. So this system picks the plies from the nest, puts it in a storage, and then starts sorting it into the right order. And then it can be used for lamination. What for us is very important is that we have a fully automated programming of this system. So it can really work on the fly. So if you change the nest or have different parts that you need to cut, the only thing that changes is the design file, and everything follows from that. So every day, every hour, you can change your operation and the total system will just adapt on the fly. And standard, you need to program a robot, do safety checks, etc. So we try to get that out of the workflow and have a very easy way of using this equipment. The second system is for sandwich panels. So you have Nomex honeycomb, and of course you have then skins. And where there are local reinforcements, you need to put in potting material. It's typically epoxy paste. It's used a lot in interiors, in trains, in aerospace. And a lot of people do that by hand. It's also toxic material, so it's not so safe to do. It's not so easy to do. So we've developed a fully automated system to do this also, again, with a robot system. So it's very fast, it's easy. And also here we introduced automated program. So again, if the design changes, it's very easy. The robot code will just be generated. And this system is also live on the JEC at the booth of Von Roll, who is one of the suppliers of this potting material. And there you can see the technology really live in action. The third cell is an automated laminating cell. So there we use thermoset pre-pack material, typically carbon fiber, but could also be with glass fiber. And then layer by layer, the robot builds up the laminate. It's additive manufacturing. And once you have the laminate finished, we go to a different end effector. We can cut the plies that we need, the shapes that we need. And then with pick and place, we can offload to the next process. And again, here we have a fully automated programming functionality. It's the same as the other systems. This system is also live here at the JEC, but then not physically here, but in our company in the Netherlands. So what we have created is a digital client portal. You can see it in our booth. You can design a laminate. The platform will give you feedback on cost and performance and production time. And when you push the button, the robot code is automatically generated, sent to the robot in the Netherlands, and there the manufacturing starts. So this shows what we're trying to set up. This is a first, let's say, example, and step by step we want to add our other production systems as well. So what you just saw were, let's say, manufacturing cells that do one task. If you think about end-to-end automation, this is an example of what we've developed as well. So this is a technology to make offshore pipes for deep sea exploration. So these are pipes, very high pressure, up to 1,000 bar working pressure, and also very long. They can be 2 to 3 kilometers long, and they're made as one part. And to be able to transport them, they are spooled on a big drum and then put on a ship. And this process uses unidirectional tapes. So we started with glass fiber, polyethylene and polypropylene, and now it can go up to carbon fiber PEEK. PEEK is not so ideal material for this application because if you bend the pipe, you need some flexibility, and PEEK is relatively brittle. But the technology can go up to these temperatures. It's with in-situ consolidation. So during the winding, we melt fuse the tapes together, and then layer by layer we build up the pipe. So we developed this roughly 10 years ago, and in that period there was no Industry 4.0. But we used digital manufacturing concepts already in that time. And I want to explain 2 examples for that. One is that the quality control of such a system is difficult. Normally in high-end applications of composites, you use ultrasonic scanning or different methods to ensure that the quality is right of the product that you made. In this case, we have a very long pipe in thermoplastic composites with a very large wall thickness. So ultrasonics don't work and other technologies are too expensive. So we qualified this application by really qualifying the process data, the quality control based on process data. We mapped the whole process. We knew when there were variations in the production data, so we also could verify that when we are within the bandwidth, the output quality is also right. And this is accepted by, for example, DNV-GL, the certification body, for these kind of, let's say, high specification pipes. The second is that we have adaptive process control, and for us that's a very important concept. If you see this pipe, there are 3 layers. So we start with the inner pipe, that's an extruded pipe, thermoplastic. Then we wind the composite layers on top, and this can be 40 layers, 60 layers, 100 layers, so a lot of layers. And then there's extrusion of the outer coating. And the extrusion process requires that the diameter of the pipe is very tight, tolerated. And the problem is that the liner has a lot of variation in dimensions, also of the length of the pipe. And the tapes that we use also have a relatively high variation in thickness. So if you add that up, and if you just make a pipe with constant settings, you end up with an outer diameter that is either too large or too small. So what we developed is a model that can predict the output. And then when we're making the layers, we adapt the process on the fly so that we ensure that the output is what we want. So we change pressure, temperature, speeds to make sure we get the right outer diameter. So that's model-based and adaptive process control. A second example, and you can also see that here on the booth of SABIC, that's our partner for this application, is a fully automated manufacturing line for thermoplastic laminates at a very low conversion cost. And the first application is for consumer electronics. So here we're making parts for laptops and smartphones. And you can imagine that the output is very high, much higher than with traditional composites, and the cost level should be very low. So together with SABIC, a new material system is developed, and also a new production system is developed. And this is now live and operating in our facility in The Hague. And it's also nominated for the Innovation Award. So after this, there will be the announcement of the winners of the Innovation Award. So we hope we receive the award. The quality inspection is very interesting. We do full inspection of the tape that goes in for defects and thickness and width variation. But we also do full inspection of the laminates at the back end. And since this is a part that needs to have a very high visual quality because it goes into a laptop, it's not so easy to know which kind of defects you can accept. So at the moment, we cut out relatively a lot of defects at the front end. But if we understand the process better, if we can adapt it, then probably we can allow a little more defects going into the laminates without compromising the end quality. And by having quality control in the input and on the output, and full control of the production line, we can again go into adaptive process control and also self-learning capability. So the line is working, and step by step we're making it much more digital. So the framework that we use is, I try to simplify it here, is we have a system, material goes in, product goes out. So the first for us, what's very important to get all the data from this manufacturing system. And with this data, we then drive a digital twin. And a digital twin is let's say, a broad container concept, but for us it's a model enriched with data analytics that can predict the output quality. And if you can predict the output quality and couple that to your control system, you get adaptive processing. So that's what we try to do. The automated programming is a tool that we also connect to this. So in principle, if the design changes, we can change the settings, and this ideally happens on the fly. And for us, it's now standard on the machines that we develop. And then we built a client portal to drive all this. So clients can go into the client portal, put in their design and requirements. This feeds into the automated programming and goes into the production machine. So this is a framework that we're building. If you look to the material, at the moment we typically just get the material. So we have to implement sensors and quality control systems to understand the properties. What we actually would like to get is also data with the material. So not just one data card or one specification, but really the variation of each batch. So when we talk to material suppliers, they always say to me, why do you need this? Because we give you material with that is certified within a certain specification. But what we like to know is the variation within that specification, because then we can tune our machines much more accurate. So if we get data from the material supplier, we also provide our products with data. You see that this data can then flow through the value chain, from material to part manufacturing to also the end use. So that's, I think, a very important aspect in this digital framework. So what I want to show you here is the client portal, how that works. This is a very simplified animation. And step by step we're building this up. So the idea is that you load your design, you load up your requirements, you design your laminate, and you get instant feedback on performance, cost, and delivery time. And if you then push the button, you push on order, then the whole workflow of programming the robot, getting the right manufacturing parameters, doing the safety check. In a lot of cases, we have also a accuracy correction algorithm on the robot, because robots are standard, not so very accurate in making straight lines, so we have to modify them. So that's all automated, and then the manufacturing will just follow on the fly. And then, of course, we can deliver the part to you, and it enables you to get full control. So you can do the trade-off yourself of better performance or maybe lower cost, instead of that we do that for you. So this client portal, there are 3 functionalities that we're building. We want to automate the engineering process that you need to do to design a good composite part. So that's about defining your laminate, doing the strength and stiffness analysis. We want to do that in an integrated and seamless workflow. The second is instant definition of production parameters, like I just explained. So path planning, material consumption, that's also done in the client portal itself. And then there's a direct output to the manufacturing system. So in the end, you have a fast and reliable and very flexible way of working. So we as manufacturer can use this portal to help you and provide a laminate or another composite part to you. So you would order online and we manufacture it for you. But actually our vision is more to help our clients, which are manufacturers themselves, using this client portal. So what we can do then is help them use a portal like this to really make ordering much more efficient. So it will boost their sales and also make their operation much more efficient. They can use it for the clients, but also internally in their own operations. So these are the business models that we are developing at the moment. If you then look to the composites value chain, and this is, maybe it's different for, let's say, the 3D printing world, but this is more the traditional value chain in, let's say, advanced composites. You have the raw materials, chemicals and fibers. Half products are made, like pre-pregs or fabrics. Then it goes to manufacturing and a tier 2 supplier, then to somebody that assembles it in a larger part, and then to the OEM. So at the moment, the value chain is relatively long and it's also fragmented. So it's not so easy to really drive innovation because a lot of parties need to be involved. So obviously, everybody wants to reduce costs. So what you see at the moment happening is people start using automation, and typically it goes step by step. You have one process that you automate and the other processes are still manually. So I think the longer vision that we see is that at one end of the supply chain, material companies are integrating. They're moving forward in the supply chain. So resin suppliers or fiber suppliers also start making the half products. And for example, what you are doing here is exactly the same. You're not selling a glass fiber, but you're selling a strand that you can use for 3D printing. At the other side, at the OEM side, you also see a pushback. So in aerospace and automotive, companies want to take control of the supply chain much more. So you see that the supply chain is shortening. And if you then develop an end-to-end automated line, so a full production line, which in essence is like a 3D printer, the parties in between that traditionally have all the know-how to do manufacturing, then only need to operate the production line. So they become more tollers. And what this enables, especially if you digitalize everything, is that material science companies can then work together directly with the OEMs and drive the innovation, create a industrialized manufacturing platform, and then just deploy it. And then it's not so relevant anymore where the manufacturing happens. At the OEM, maybe the material supplier will do it, maybe a toller. It's, let's say, independent of who produces the part. The knowledge is embedded in the system itself. So this is where we think the future is for the composite manufacturing value chain. So I would like to end with a small animation that explains this vision. It should have sound, so let me try if I can start it up. And then we will listen to this vision that we have. Sound should be a bit more, I think. Can you hear it? No. Okay, I'll explain it by myself then. So composites have a lot of benefits. So lightweight, durable, very flexible. So in many applications you want to use it, but it's expensive to use because it's a complicated technology. So it's not really the case that you can do mass customization like you're doing in 3D printing.
To enable mass production of composites and make it affordable, we need to automate and industrialize to disrupt the value chain. At Airborne, we have a vision on how to achieve this. First of all, you need to automate your production process and transform current production steps into automated solutions. As building blocks, they can become a fully integrated production line, managed by one OEM. But automation only gets you so far. If you radically want to change the price levels, you need even more disruptive measures. Mass customization for every industry can only be affordable if you automate and digitalize. Smart and self-learning algorithms can add or remove individual building blocks from the assembly line, creating endless production possibilities, resulting in custom-made products for the masses, produced next door in your local 3D print shop. Our vision is a digital composite technology platform where the end consumer submits an order online and adds the design requirements. These will be digitally checked and sent to a nearby automated production line. As Airborne, we work on shaping the value chain of tomorrow. We envision a future with digitalized composites technology platforms. This will enable mass customization of composites. Our solutions will cut production costs by 80%, making it possible for all industries to enjoy the full benefits of advanced composites.
So that's really the vision that we're building. We're not there yet, we're going step by step, but we really are strong believers that this is the future of composites. And it's very similar to the vision that Ultimaker has, but then really from a different angle of the composites industry. So thank you for your time, and I'm happy that I could present this here. And thanks for the invitation. Questions or? Okay.
Does anybody have any questions?
Okay. Good.
Okay.
I think you just wanted to speak.
It's okay. Just leave it. Just leave it.
Yeah.
So with that, I think we come to the end of the session we put together. So we started with this thing about how do we start to change the conversation we have as an industry with a customer. I mean, really the point I was making when I started with, this is not, we should stop talking about ourselves and we should talk about how we're actually going to enable our customers to do things that they actually want to do. How can we help them make the impossible? And I think as we've talked through the presentation from Paul and the presentation from Marcus, you can see that there's this movement towards different ways of thinking about the composites industry. And really, I think it's something that we continually need to reflect upon, which is our job is to make the impossible. And that's going to involve technology changes from fiber suppliers and resin suppliers. It's going to involve technology changes from converters. It's going to involve technology changes from machine producers. But essentially, we're going to transition towards something where the integration of technology and manufacturing is going to become absolutely critical to enable our customers to do the things that they want to do. And with that, I just leave you with the thought that really, as you walk out of here and you walk into the stand, just reflect as you walk past the stands how many times we're telling each other about what we do every day, but not about what we can do for our customers in the future. And with that, I thanks for your attention, and hopefully Marcus is going to win the Innovation Award. Thank you.